Hi everyone, I'm Jorge García Condado, and I research how we can help clinicians use artificial intelligence to study neurological disorders. And today I'm here to clarify some doubts and answer some valid questions you all may have about artificial intelligence. So let's start from the beginning. What is artificial intelligence? Well, I wish I had a simple answer I could give you or a boring textbook definition, but many have tried to define what artificial intelligence is and failed. Because even defining what intelligence is a very complicated task. So imagine trying to define what artificial intelligence is. So what I want you to do is to close your eyes and for 30 seconds, think about what artificial intelligence is for you. This could be an image, this could be something from a movie, a video, a concept, something that you say is artificial intelligence. Okay? So I'm pretty sure a few of you have thought about this humanoid robot idea that we have of artificial intelligence. And this is actually very far from the truth. Actually, robots are very, very difficult to train with artificial intelligence. You might have seen the Boston Dynamic robots that jump around and do flips and do all of these kind of parkour tricks. Well, actually, they weren't trained with artificial intelligence because it was way too difficult. The physical real environment is a very complicated place. So there is something that you interact with every day that is artificial intelligence. And it's right here. It's in your phone. When you take a picture and it gets processed with artificial intelligence, or your spam filter decides whether something is spam or not, or using TikTok and being addicted to it all day. And that's all thanks to artificial intelligence. Right now, we interact with artificial intelligence on a daily basis, but it is hidden from us. And that's why there is a big misconception on what artificial intelligence really is all about. So, I'm also sure some of you might have thought about this, about the movies and having Jarvis from Iron Man, an artificial intelligence that is able to do absolutely everything. It is able to adapt, to overcome any situation, to do multiple tasks at the same time, even tasks it's never done before. And this is what we would call artificial general intelligence. General because as a human, it can adapt and it can do several tasks very well. It may even be able to do several tasks better than humans do. And this is the holy grail of artificial intelligence. This is what we are all aiming for. But the truth is that we're very, very far from this. This is what we're trying to do. But right now it belongs in movies and science fiction. So what we're going to be talking about today here is something else. And that something else is artificial specific intelligence. And why specific? Because right now, specific artificial intelligence is what we have. It is able to do one task and only one task. It does it very well. It can do it very well. But it can't do other ones. And here we have an infographic from the community Better Images of Artificial Intelligence that I encourage you to look to afterwards. It's a community that is trying to demystify what artificial intelligence really looks like. So what does artificial intelligence look like? Well, it is maths, yes. Artificial intelligence is based on maths. We use maths to train it, and it is part of it. We can't get rid of it. And as humans, it's based on patterns. Humans use patterns to predict new things, and artificial intelligence do the same thing. But there's a big difference, and that's all about the scale. Humans can learn with a few examples, a few hundred examples, a few thousand examples maybe. But artificial intelligence, to do the same task really, really well, require not thousands, not even tens of thousands, but at least hundreds of thousands or even millions of examples to do the same task that a human needs. Hence, these are very complex systems. These algorithms are very complex, and they are measured in the number of parameters they have. And we're talking that the newest models that you've all probably seen in the news recently have millions or even billions of parameters to make it work. And yet, they're still very narrow. They can only do a very specific task. You may have heard that sometimes they can be adapted to do a task that they weren't intended to do, but this is actually using a few tricks. It's not that they were specifically built to do those kinds of tasks. And that means that they're non-human. And this is important to remember because everyone sort of thinks of artificial intelligence as, hey, I'm intelligent, therefore the artificial intelligence should behave like a human does. But it shouldn't, because it is not a human and it's not intended to be a human. So it has non-human capabilities and doesn't think like a human because it's artificial, which is beneficial because we can use computers and we can build even bigger computers with more and more computing power to solve tasks that we weren't able to solve previously. But, and this is important, we must always keep in mind that artificial intelligence is built for humans. And therefore, whenever we build an artificial intelligence, we have to take the human factor into account. Because if not, we can end up with our current situation where people don't trust artificial intelligence, don't know what artificial intelligence is really all about. And this can bring some big problems. But it can also be the tool in the future to uncover new insights that were never known before. And in the same way that humans learn in different ways, so do artificial intelligences. So let's talk about the different ways that artificial intelligence can learn. In the same way that a teacher can deliver content in different ways and students learn and have different studying skills that they apply, artificial intelligence is the same. And we have three things. We have supervised learning, and reinforcement learning. So let's go over these three. And yeah, I took the chance to put some pictures of cute dogs and cute cats, because why not? So with any artificial intelligence comes the first thing, which is a data set. And in these data sets, we have data points. So in this case, the images of our cats and dogs. But because it's supervised, we also require labels for these images. So in this case, here we have dogs, and we've labeled them dogs manually, and cats, and labeled them cats manually. So what we can do is we show the picture of the cat or the dog to the artificial intelligence. We ask it whether it's a cat or a dog, and if it gets it wrong, we tell it it's wrong. So for example, we take this cute picture of a dog, and we feed it to the artificial intelligence, and we ask it, is it a dog or a cat? And if it's a dog, we tell it, okay, you've done it right. If it's a cat, we ask it to change its internal workings so that it outputs a dog. And we do this for thousands and hundreds of thousands of images. And we don't do it once, but we do it multiple times with the same images repeatedly until it achieves a good accuracy of identifying dogs and cats. And that's supervised learning, where we have data points that are labeled and we can sort of guide the algorithm to what we actually want it to do. So what's unsupervised learning? Well, now imagine we don't have any labels and we just stick all of the pictures of cats and dogs together. And we ask the artificial intelligence to divide the images into two groups. And we ask it to look at what the images contain, at the different parts of the image. So we tell it to look at how pointy the ears are or how round the eyes are. And we ask it to divide the images into two groups according to characteristics that the images share. And so hopefully what the algorithm should do is divide the dog images to one side and the cat images to the other. But, and here's specifically why I've written group 1 and group 2, the artificial intelligence has absolutely no idea that group 1 are dogs and group 2 are cats. It just knows that those images contain things that look similar in group 1 and in group 2. And then it's the human's task to come and analyze the data and say, actually, group 1 are dogs and group 2 are cats. But the human has to be involved to give some meaning to that data. And then finally, and one of the coolest ways of learning, is reinforcement learning. And reinforcement learning is learning very similar to what humans do. It's a kind of trial and error basis of artificial intelligence. So how it works is the following, and we're going to use an example to showcase this. We have an artificial intelligence that we're allowing it to draw things, to scribble, in the same way humans try to draw art. And what our task is we're going to let it draw loads of scribbles. And afterwards, we're going to tell it the scribble that looks more like the thing we want. And so, for example, in this case, we're getting it to draw a dog. And so we tell it that the thing that looks more like a dog is this one. It has 4 legs, it has an eye, it has an ear, and it kind of looks better than any of the other drawings. And hence the artificial intelligence starts to scribble again, and we tell it again the thing that looks more like a dog. And as time passes on, the artificial intelligence learns to scribble better and better and gets better and better at drawing pictures of dogs. But it's not yet there, because unlike humans that might take a few hundred tries, a few thousand tries, artificial intelligence takes a lot of tries. And we're talking, in some cases, they might be months learning this kind of things. But afterwards, after we tell it continuously what the correct image is, or the image that looks more like the thing we want, the artificial intelligence ends up drawing very cute pictures of dogs. And that is reinforcement learning. So, I mean, we've been talking about cats and dogs now for a while, but we're here looking more at medical stuff. So let's look at 3 examples, one of each kind, in which we can apply this learning to things in medicine. And the first one, which is the standard one when talking about these things, is imagine a dermatologist. And normally they have to look at skin lesions and decide whether the skin lesion is benign or malignant. And dermatologists do this every single day, and they're very accustomed to it. So it means that many of them have taken thousands of pictures of these things, and they have labeled themselves whether it's benign or malignant. It's in the clinical history. So we can take these images, we can first train a first artificial intelligence to find out where the skin lesion is. Then from these skin lesions, we extract features. We extract things like the color, the shape, the size, and use these features in a second artificial intelligence algorithm to determine whether the skin lesion is benign or malignant. And this is very tedious work that could free up time for the dermatologist to have a better human connection with its patient, to explain to the patient what the actual outcome is and how it relates to how the disease is going to progress or not. And this is where artificial intelligence can come in really handy, because it's here to help remove tedious work so that we can make medicine more humane. So, now that we know how it could be applied in a clinical context, we can also look at how it is applied in research. And in this case, we're going to be talking about unsupervised learning, and something that has been developed in the Cortez lab recently. And that's a study where they took a set of autistic patients, and in this case, they asked the artificial intelligence to group the autistic patients based on how their brain was connected. And the artificial intelligence decided to divide them in 3 groups. One with a hyperconnectivity, their brain was more connected than normal compared to the controls. Then a group that had a normal connection, and another group that had a hypoconnectivity. The brain wasn't as connected. And the interesting part was that after further analysis of this group, they found out that one of the groups had some mutations in genes involved in cholesterol. And hence, yes, we needed the artificial intelligence to come in and separate the humans based on how their brain looked, but without the human afterwards coming and looking at the genetic data or what does the separation actually look like, we wouldn't have this powerful insight. And now, finally, I want to show you a bit about reinforcement learning, a very cool video that is one of the things that got me into artificial intelligence. And this is something that they developed in the University of Vermont, where they used artificial intelligence to build the first living robots. And here's how the task went. They let the artificial intelligence design robots based on 2 cells. Cells that could either stick together or cells that could wiggle around. And they let the artificial intelligence, in a simulation, pick out the robots that move the farthest. And here is the result. So imagine how cool this is, that we're able to get an artificial intelligence to find out for us robots that work and move around on their own, that can be used for multiple purposes. So, I mean, we've been seeing how we can train artificial intelligence, the different ways that they learn, but we haven't talked yet about what tools we actually use. And here you've probably heard many of these buzzwords because many people use them every day to talk about their algorithms, and that's machine learning and deep learning. So let's take a look at what machine learning and deep learning is. We won't go into technicalities because it's actually pretty boring, it's very mathsy, but let's look at what they actually mean. And the first thing we want to say about machine learning is there is a big discussion of whether it's just maths, and they've had a nice branding done to them, a nice marketing campaign to say that it's actually machine learning and it's a new technique. But actually machine learning and the tools we use have been there for a few decades at least. And basically machine learning is just getting an input and a function that transforms that input into the output, the label or the variable that we want. And we have several ways of doing it. We can have parametric methods that make some assumptions about the data. So for example, linear regressors that I'm pretty sure most of you know about, which is just using a linear equation saying something is correlated to something, kind of counts as a machine learning algorithm. And that would be parametric because we're making an assumption that the data is linear. And we can include some more assumptions. If, for example, we're talking about circadian rhythms, we can maybe use the assumption that we know that it's a rhythm and therefore it should be cyclical, and our model should have some cyclical component to it. But there is a more interesting way of doing it, which would be with non-parametric methods. And what are non-parametric methods? Well, non-parametric methods make no assumption about the data. They just search for patterns in the data and then use those patterns to reproduce the findings that they have. So for example, the simplest one to understand is the k nearest neighbors, where imagine we have a patient that we want to diagnose, and we've extracted certain features like its blood pressure, its BMI, and a set of features. And then we look at the k people that have a very similar clinical history to that patient, and we assign to that patient the disease diagnosis that the other k patients had. And it's that simple. And therefore, we're making no assumption of the patterns in the data, but the patterns are inferred directly from the data. And there's a whole array of these kinds of algorithms. They all have their own technicalities. But what I want you to remember is that machine learning is just a very simple mathematical function. It's a vast array of tools that have been available for quite a while. So, what's the difference then with deep learning? Well, deep learning is a subset of machine learning. It actually counts as machine learning. But, as we've been talking about, machine learning requires us to make some decisions about feature extractions, which features we want to include and which features we don't want to include. So, they came up with this idea of, wait a second. What if we let the artificial intelligence itself decide the features? That it learns to represent the data in a way that is meaningful and then uses that representation to come up with a classification. And that is why it's deep learning. Why is it deep? Because obviously to learn to represent this data, we need much wider, much bigger algorithms that have more complexity in order to learn this representation. And that's why it's called deep, because it has more layers to it. But it is still machine learning. So, I know now that you know what machine learning and deep learning is and kind of how it learns these representations. The obvious next question is that everyone has about artificial intelligence is it a black box? Everyone thinks that artificial intelligence is a black box. And this has been something that the artificial intelligence community has struggled with for a very long time, to explain to everyone that actually we know way more than what people think about how these things work. Mathematically, we're very sure of how they work, but that is a very complicated and very boring topic. So I'm going to show you 3 ways in which we're pretty sure that the artificial intelligence is not a black box. I'm going to try and convince you. And the first way is talking about some simple machine learning algorithms that have direct interpretability. We know how they're making their decisions. And the first one would be a decision tree. In this case, the artificial intelligence builds a sort of logical statement where it goes, does the patient have low or high blood pressure? Does the patient have a very high BMI? Does it have high levels of glucose? And after answering all of these questions, it comes up with a label for the patient. Hence, we can directly ask the artificial intelligence, tell us the logical flow of how you came up with this decision. And we can understand how it came up with its decision. If we have, in this case, a logistic regressor, where it's looking at the different variables linearly, we can see the weight or the importance that the algorithm gives to each feature. And therefore, we can see if these features correlate with what medical literature says. Does medical literature say that glucose is related to a certain disease? Yes or no? And hence, the doctors can come in here and help us decide whether this artificial intelligence is sort of making sense with the decisions it's actually taking. But yeah, I mean, if you all can see a flaw here is that we're talking about very simple algorithms. And the ones that are more useful are more complex and more deep in nature. So let's look at how we can actually explore what they're doing. And for that, I'm going to use the example of ChestNet-X. ChestNet-X is a convolutional neural network that is able to identify 14 different pathologies given a chest X-ray. And it does so to a very good accuracy. But the researchers were very unsure of how it was making this decision. So they came up with this experiment. They gave the same chest X-rays to a set of radiologists and asked the radiologist not only to give a diagnosis, but to point out and circle in the chest X-ray how he was making the decision. What were the features they were using to make their decision? And afterwards, they used a tool called activation maximization to look at which places the artificial intelligence was focusing on in the image to make its decision. And those are the areas you see in yellow. And as you see, the artificial intelligence is looking at the same areas that the radiologist is using to make their decision. So, although we don't understand exactly how the artificial intelligence is making the decision, we do know that it's taking the same features that the radiologist would take. And hence, we can't try and attempt to understand perfectly how the artificial intelligence is making the decision, but at least we're sure that it's looking at the right place. And then a very cool project that I also encourage you to look forward to afterwards is the OpenIA microscope. And this was a big project that OpenIA, Elon Musk's artificial intelligence company, used to look at how machine learning methods, and specifically deep learning methods in convolutional neural networks, at different stages of the process, the kinds of images that are evoked. And here is where the famous Donald Trump neuron or the Jesus neuron comes into play, because as you see, some parts of the algorithm react very strongly to a certain input. So we see here in one of the corners some buildings, another part of the algorithm that reacts to eyes, to flowers, to something that looks like, TV things from the 80s, and so on. Hence, we have now powerful tools to dissect at each stage how the artificial intelligence is seeing each of the images. And hence, this is not so much of a black box as people tend to think. And finally comes the question of, well, what if we actually can't do any of this? We can't see how the algorithm is doing, we don't really understand because it's non-human and doesn't process information in the same way that humans do. How do we get a sort of uncertainty quantification? And this actually has two very easy solutions. We have been studying probability for centuries now, so we can include probability into our algorithms so that instead of getting a very specific value, we get a range of values. And then we decide whether this range is too big, and if it's too big, we'll make a decision on our own because we know that the artificial intelligence isn't sure of what they're doing. Or, on the other hand, what we could do, and going back to the case of dogs and cats, is include a third label, which is unknown, and give it images of people, landscapes, noise, anything we can imagine. And therefore, when the artificial intelligence is given an image that they don't know what to do with, it'll tell you, hey, it's unknown, I don't know how to deal with it, it's your problem. And hence, even though in this case it will be a sort of black box situation, we are at least sure that we're making the correct steps to identify when the algorithm doesn't know what they're doing. So, where does this all take us? Where is the future of artificial intelligence in medicine? Well, it's obviously clear that medical doctors have a good medical expertise and engineers have a good mathematical background. So together, they can work to improve and get better artificial intelligence systems. But I know most of you here are doctors and clinicians. So how can you actually help? Well, there are three obvious ways in which you can help. And the first way you can help is asking the question, is it useful? Engineers, and I myself, love to solve problems. But sometimes we solve problems that don't exist, or even worse, we solve problems that weren't even there in the first place. We create new problems. And hence, clinicians can come and say, actually, you know what? That's not useful for me. Don't do that. Don't bother spending loads of time on that because it's not going to be useful. Then, as we've been talking, sometimes we have to make decisions about which features to extract or not. And here's where clinicians can come and tell us, with their medical expertise, whether something is relevant or not. And finally, and most importantly, it can help us answer the question, what does it mean? We're engineers, we don't have medical expertise, and therefore it's very important that clinicians are involved so that they tell us what this actually means in clinical terms. So, the problem is that with new technologies also come new challenges that we have to overcome. And the sooner we start talking about them, the sooner we can start dealing with them. So we have to talk about ethics. And in this case, I want you to consider the following scenario. We have an engineer and a clinician. And the engineer has developed an artificial intelligence that helps the clinicians give the right amount of drugs to each person. Because this is a drug that is very difficult to get the correct dose right. But the artificial intelligence has been trained with a lot of data and does it really well and has been approved. And so the clinician starts using it in his practice. And after a few years, the clinician realizes that although it was working really well, something's starting to be off. Something's not working anymore. And so he goes back to the engineer and asks him, hey, can you have a look at this? And the engineer goes, "Aye." And he realizes that there's been a data shift. And what's a data shift? A data shift is when the data you use to train the artificial intelligence no longer represents well the kind of data you're predicting, you're trying to make predictions on. And therefore, the algorithm starts to fail. So here comes the question. Is it the responsibility of the clinician for not having realized soon enough that the artificial intelligence wasn't doing the thing it was supposed to do? Or was it the engineer because they forgot to somehow put something in the algorithm that detected a data shift? Which brings up the obvious next question. How do we regulate all of this? Because regulation always lags behind technology. And there is a clear question in all of this, which is, when is the algorithm good enough? Is it good enough when it's doctor level? When it's better than a doctor? Or what about the case where a doctor is not available? The artificial intelligence is not as good as a doctor, but good, that it can maybe save lives in those places where doctors or clinicians are not available. So it comes up with the next problem that we have to talk about, which is how we deploy these things. How do we make it fair? Because obviously there is a big problem with artificial intelligence, and it's that it requires a lot of money. Because you need a lot of computing power, you need to store the data sets, and all of these problems that come. And it also brings up the next question, which is how, okay, maybe we can train them here and then deploy them elsewhere. But how are we going to deploy them elsewhere if they don't have the resources? Or a more important question, what about bias? Because there is a big problem here that people tend to think that artificial intelligence, because it's non-human and doesn't have emotions, is the most unbiased thing in the world. It doesn't make errors, it doesn't fail, it's very, very fair. And the truth is, it's not. Because artificial intelligence learns from patterns, and data has the patterns that humans have embedded in them. And medicine is, I think, one of the perfect examples to showcase this in this case. Because most of the medical datasets, the big medical datasets that we can actually use to train artificial intelligence, have a big bias because about 90% are white and European. And we have the big problem that the populations, the black populations, the Asian populations, are not well represented. So we don't know how the artificial intelligence is going to interact when it sees one of these patients that it hasn't seen as many examples of before. And this, hence, brings up the same problem of deployment. So does that mean that we're only going to create artificial intelligence for people in places like Europe, America, and so on, and never deploy them elsewhere? Or are we going to take the time to try and fix these sort of problems? Okay? But it doesn't mean that, and we have to solve them now, because artificial intelligence is already here. And for that, I want to talk about what has been dubbed the method of the year this year. And it is the first method that includes an artificial intelligence, and that is AlphaFold. I don't know if you know what AlphaFold is, but I'll try and explain really quickly. There is this problem in structural biology where we didn't know how the amino acid sequence related to the final structure of the protein. And for a very, very long time, scientists were working very hard to try and understand it. And so here comes DeepMind and trains a massive deep learning algorithm and effectively solves this problem. We really don't know yet how it works, but it does it very well. It is able from the amino acid sequence to get the structure of the protein. And what does this have to do with medicine? Well, actually, it can exponentially accelerate the development of new drugs. Because imagine we have a protein that we want to target. We can build a model of the structure that attaches to this protein, and then reverse engineer, using AlphaFold, what the correct amino acid sequence should be so that this structure sticks to the other protein. And hence, we can get medicines, and even medicines specifically targeted to specific people, very, very fast, thanks to these new breakthroughs. But what about medical devices and clinical practice, which is what we were talking about today here? And here we're going to look at the Food and Drug Administration from the US, because actually they have the most data available on what the devices that have artificial intelligence or machine learning enabled devices. And currently, as of October 2021, there are 350 of these devices. It might not sound like a lot, but think about it. Artificial intelligence is very, very new. And there's already 350 of these devices that we've deemed are good enough for clinical practice. And yeah, I mean, it's obvious if you look at the top that radiology dominates the field. And it is for very obvious reasons. The computer vision community is very active in artificial intelligence, and radiology lends itself really well to these kinds of algorithms because we have the trained label data, and it is kind of the task that artificial intelligence community is really accustomed to. But what I find really exciting is that we're seeing that there's devices in everything, from orthopedic to neurology, hematology, even plastic surgery or general surgery, and dental. It means that we're seeing the first boom. It's starting to happen. Artificial intelligence is coming. But, and here's a big but, we're not ready yet. I don't think so. And here is a very good case to showcase why. And it's the COVID-19 pandemic. And it's kind of bringing everything of this back to the real world. And it's the fact that after a big review from the University of Cambridge and also from other scientists in the US, they researched over 100 artificial intelligence algorithms that were built to try and detect and prognosticate COVID-19, but failed miserably. Failed miserably to the level that none of them were deemed for clinical use. Most of them weren't tested enough. Most of them didn't even have the correct metrics. And only 2 of them were deemed to be potentially worthy to keep looking at. And hence, this comes to show that there is a big hype around the artificial intelligence community, that we are trying to get in there, trying to get in with, into the clinical sector. But we have to stop and think, and start to work hard with the doctors so that the algorithms that we bring to the table actually work for them. And the COVID-19 pandemic is a good example because we have been working with them and we've now learned what we shouldn't do. We shouldn't take this as a terrible failure. I mean, none of them worked and none of them were of usefulness for clinicians. But from all of this, we can learn what we should do next. And hence, I want to finish off with a quote from the father of artificial intelligence himself, Alan Turing, which is that if a machine is expected to be infallible, it cannot also be intelligent. In the same way that we don't expect humans to make no errors, we can't expect artificial intelligence to be perfect every time. And here we have a great opportunity to make sure we remove the tedious work from doctors and allow them more time to make medicine more humane and less robotic. Thank you. Any questions? No questions? No, oh, there. Wait.
Thank you. Well, I have a question because I am trying to understand what have you said in more or less one sentence. So you have mentioned that artificial intelligence depends on parameters. So the greater the number of parameters, the greater the accuracy of the prediction.
No.
In a way.
No, this is a complicated subject. So the problem is, if you don't have enough data and you have too many parameters, the artificial intelligence starts to overfit. And what is overfitting? It has enough parameters that the artificial intelligence can learn to memorize the data. And so when you feed it a new data point, it doesn't know what to do, because instead of learning to recognize patterns, it's learned to memorize data. And therefore, when you give it a data point that it's seen, it gives you a perfect answer because it's memorized it. But when you give it new data points, it actually doesn't know what to do because it's not in its memory. And hence, there is a kind of validation that goes on when you do this artificial intelligence to try and find what the optimal number of parameters are. You separate the data set you have actually into 3 groups. A group that you're going to use for training, a group that you're going to use for validating. So for these kinds of problems, let's look at how many parameters we should use. And once you've tested all of that with the training and validation parameters, you use the test cases to finally report in your scientific, in case of a scientific communication, what your actually true accuracy is.
Okay. So in other words, you have to have a proportion between parameters and number of data to feed the algorithm on that.
Exactly.
Okay.
So for most algorithms, like the big algorithms you might have heard of, like GPT-3, that is a big language model that is able to generate text that is undistinguishable from humans. They use millions, I think, or even billions of parameters, but I think they have the whole of Reddit downloaded. So we're talking that they have like at least 100 or 1,000 times more data points than parameters that you have.
Correct. Thank you.
Any more questions? Cool. So thank you very much, and well, thank you to La Caixa Foundation because they finance my research, and enjoy the rest of the day.